Happy VW Day, everyone. Welcome back. Today's the last day you could drop the course without getting a final grade assigned. One bit of knowledge that I wish I had when I was in your position is that today is indeed the last day you can drop. It's not that you have to drop before the VW date. The VW date is the last day you could drop. Awesome. So term test marks have been released. You should all have emails about that. If you have any questions, especially if any of your answers got lost in the scan, or if you disagree with the markers on how something was graded, let me know. So to start today, we're going to pick up where we left off on what is now finally today's lecture. I'm going to show you all an example of using the data structure that you're going to be implementing in assignment 3, and also visualize how it's actually working. So we're going to SSH into Aviary as per usual. And then there's the file that I'm going to be showing off. That is on UMLearn. At least I think it is. I'm going to both show you where to find the file, and then if the file doesn't exist, that'll be my reminder to upload it. By the way, the sample solution for assignment 2 is posted. So you should be able to find today's code under Lectures, Week 5, Lecture 17, Using Zones. I think I'm going to need a second terminal window, actually, because I'd like to, emails. But I'm on Do Not Disturb. That must have been someone else. Or I just had my volume on. Whatever. Let's go with one terminal window for now, and I'm just going to show you the code before we execute it, and then basically step through it and draw some wonderful pictures. So you don't need to worry about those strings and pointers at the beginning. The first thing of interest is line 15, a call to the zone's constructor. We pass 16 into it, which means we allocate 16 bytes, which is space for 16 characters. And then we allocate space for an 8-byte string, and then copy it into our zone. Then we allocate 5 more bytes, and this is just an array of numbers. Note that the chunk of memory that the zone uses, that's basically one big array, but we're storing both letters and numbers in there. They're all of type unsigned char because we want them to take up 1 byte each, but we're interpreting them differently as either numbers or characters in a string, depending on the type of the pointers into that big array. I'm going to go through this again in more detail as I'm drawing, by the way. The real important part will be me explaining how the zone keeps track of the metadata for memory allocations, like what has been allocated and where. Anyway, we then free the original string and allocate space again. Where will this space be allocated? It depends on the allocation policy. First fit is really simple, but I'll demonstrate that later anyway. And then we just copy the string into that too. And then we print some info about the zone and destroy it. This comment demonstrates the utility of zones. We kind of forgot to free everything except copy 1, which we free on line 39. But it doesn't matter because we control that entire chunk of memory and we're able to free it all at once on line 52. And then we have the memory addresses of everything. So you don't need to worry about those exact values, but notice how some of them are pretty similar to each other. They're close. So the two originals are both at memory regions with the last few digits being 400 and something. And then the copies have the last few digits, F2D0. And these copies and the zone data actually have the same address because the first copy is written to the start of the zone data, then it's deallocated, and then the copy Kraken is then written to the space that used to be filled up by hello. And then just more metadata. I totally neglected this while doing the assignment myself. Don't. This is pretty useful info for debugging. If something's wrong, you should probably check the output of zdump. I think all the rest of this stuff is pretty straightforward, except active 1, that's a bool. The sample solution doesn't bother doing nice bool printing like you did in assignment 1, so it's anything other than 0, thus it's true, and active is just whether the zone has not yet been freed. So I kind of wish I could show both the document camera and the code at the same time, but unfortunately technology has not progressed that far yet. And I'm probably just going to have to rapidly switch between them. I also got new pencil lead. So that tape metaphor for memory is going to come in real handy here. Each slot of the tape represents 1 byte, or the size of 1 unsigned char. So we'll start by just drawing our zone. Five, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, sweet. The squares clearly get narrower as they progress. Don't worry about it. And then The exact addresses, once again, aren't that important, but I'm going to try to be at least a little bit accurate. So zone data starts at 0x 646BC 0A4F2D0. Yeesh. I'm probably going to just refer to them as squares 0 through 15, but it's cool to know that this has an exact address somewhere in our computer's memory. So we have the result of the constructor call on line 15. We're just going to assume that all of the allocations succeed. Your zalloc function should have something similar to malloc in that if it can't allocate space, it returns null. And I've never seen malloc fail myself, but your zalloc will more than likely fail at some point, especially if you're making small zones and want to see whether the code for handling allocations that don't have enough space for them works. So we allocate 8 bytes. We assume that it works. And then we copy the string hello with 2 exclamation points to the buffer. The whole thing is empty, so the first fit allocation policy just gives us the first slot of our tape. Cool. So we've copied the string to the memory location that we're pointing to. Probably going to emphasize again and again and again, everything's a number. Let me just look up that good old ASCII chart. Capital H is 72 in decimal, and lowercase e is 101. So we could have just as well written 72 and 101 and so on for the different ASCII values, and that would be just as accurate. Letters and numbers, in our case, are different representations of the exact same thing. So zalloc returns a pointer to the allocated memory, just like malloc does. So we're going to keep track of that too. So copy 1 points there. This is going to become a mess of arrows. Actually, I'm going to draw it in a way that'll give me more space to work with. There we go. So far, this is probably pretty clear from the interface, but now I'm going to give you some insider information about the implementation. You're going to have to track what blocks are where and how big they are. And how are you going to do that? With a linked list. So internally, there's going to be a linked list node. The zone is going to have a head pointer, of course. And each node of the linked list represents a single memory allocation. One, two, three, four, 8. You could imagine an arrow pointing nowhere as pointing to null. So this linked list node represents the copy1 allocation. In your solution, your linked list node struct class will probably have a lot more metadata than this. But for the sake of this explanation, all I've thought of so far is start, size, and next. So that's what we're going to go with for now. And then we just copy, or we print the contents of the strings and their addresses, no big deal. Next, we allocate 5 more bytes. The first fit allocation policy makes this real easy. We just, well, actually, the exact implementation details are up to you. But it'll probably look something like this. You start at the head. Note that the first block starts at the first address and has size 8. So maybe the 8th slot is free. And then you keep going through the linked list, cataloging basically what areas are free and how large the free spaces are. And then eventually, and then once you find a space that you know the allocation will fit in, mark that one as where you're putting stuff. As you keep allocating and deallocating memory, the ordering of the linked list might get a bit messy. So it might be useful to sort them so that maybe instead of having the linked list nodes in chronological order, like the order that the allocations were allocated in, you might want to make it so they're ordered in terms of where they are in memory. Nothing I'm saying right now is what you have to do, but things that might make your life easier. There are, of course, a million different solutions to every problem. So anyway, we allocate 5 bytes. So internally, everything above local variables happens within our zones implementation. We make a new linked list node. And then that is what our zone implementation is going to look like as of this line. And then we treat it as an array of numbers and write a bunch of 42s. And of course, I've already emphasized that jars are just numbers, but I'm curious of what 42 is as a character. Asterisks. Maybe we're writing a swear word. I don't know. Oh, and let me just update our local variables as well. So notice that the local variable points to the same place that one of our linked list nodes points to. That's intentional. Your client will want, like the person working with the code that you wrote, writing new code, the client will want to keep track of the pointers that they're given, and you will want to keep track of the pointers that you have given out. Now, we need to see what happens when we call zfree. I'm just struggling internally on whether I want to start an entirely new piece of paper, because of continuing the demonstration is going to involve erasing some stuff. I want to make sure that it's clear for people at home. Yeah, I'm just going to recreate it real quick. And we're back. So we have zfree on copy 1, which means that this pointer, whatever you want it to point to represent that, is going to get deallocated. As always, the exact ways in which you choose to implement this can and will be different, but one way you might want to do this is to take the copy1 pointer and then just do a linear search through your linked list and find a node that has a start property that's identical to the pointer that you just received. So copy1 points here, the first node points here. We found a match. Die. So now the pointer the block that corresponds to the numbers pointer is now the head of the linked list. And the memory that was in our allocation, that hello string, you could do what you want with it. I would maybe recommend zeroing out that memory, just going through this and writing 0 to every space. I would even maybe recommend doing that at the start. These blank squares have whatever was allocated in memory before we got here, but you might want to make it all zeros just in case. And now copy1 is a dangling pointer. It points technically to hello, but that memory could get overwritten at any time. Very dangerous. The client should probably set copy1 to null, even though it totally doesn't in this example. So now we're going to allocate a new, I should find better words for this, a new allocation, I guess. Allocate a new block? I don't know. Copy2, 7 bytes. The first fit algorithm does its thing. It finds that there's a block that starts at whatever number this is, probably index 8, and has a size of 5, meaning that there's a block of 8 free slots right before it, which allows the first fit algorithm to identify that as the first part of memory that can hold what we want to allocate. Success. So we make a new block for copy2, a new node. Start pointer points to the beginning of the block that we've newly allocated. Size is 7, and next points to nothing in particular. Classic linked list. Now that we have copy2, I should totally write that down in local variables. That isn't confusing at all. You can follow arrows. Computer science is just boxes and lines. Ask Rob. So we copy the Kraken string into the memory pointed to by copy2. What exactly is the Kraken string? Oh, it's just Kraken with a capital K. our pretend implementation didn't zero out that memory, so we're going to just have to overwrite the characters that were there before. And yeah, it just works. Notice that we have 1 byte or 1 memory slot of space that we're just doing nothing with. If the client ever wants to allocate a block of size 1, it would go there. But in all other cases, we're now facing a bit of fragmentation. If this keeps happening, we'll have a bunch of very small free spaces, and even if there is enough free space to hold a big allocation, if it's all spread out, it'll be useless. That's kind of a thing you don't need to worry about, but it's a thing that happens. And then I think beyond that, there's nothing else worth drawing. After we copied the string on line 44, we just print out the strings and the pointers to them, and then print info about about the zone in line 50, and then destroy it on line 52. I should point out as well that this is just as vulnerable to buffer overflows as ever. We could have written, release the Kraken instead of just Kraken, and store copy. It would have happily overwritten our little array of 42s here. That is also not really your problem. This is C, and if the client misuses your code, it's your fault. It's their fault. In a more realistic implementation, it would be good to verify on write that the client isn't causing a buffer overflow, but you could imagine that maybe being a bit difficult. Especially if the user writes to the middle of an allocation. I certainly can't think of any way right off the top of my head to tell which allocation a user is writing into. I guess you could probably note that this entire region is full based on this linked list metadata, just the same way that we're figuring out which spaces are filled up for the sake of first fit memory allocation. So it may be possible, but it sounds like a real hassle. And more importantly, the assignment outline doesn't say you need to do it. So I think that's all for our arts and crafts session. Again, make sure to implement zdump early. It's very useful. And I'll post both of those drawings to the course website later. So, question?
The recordings don't show the camera of the paper, right?
No, it doesn't. So, yeah, if you're watching at home, you'll just see a bunch of stalling on a single slide and me describing a drawing. I looked into it and I'm not able to record the document camera, so this is the best I could do. So I believe this is it for today's lecture. We covered the rest of this in class yesterday, so we're going to keep going slightly farther ahead. Yeah, don't use extern. You should know about first fit memory allocation. And we're about to do some more pre-software engineering. So, at the end of tomorrow's lecture, you should be able to describe the benefits of modularity. That's talking about modular design, as we have been covering for a while, interface versus implementation. This goes deeper into that. And use simple metrics to specify the degree of independence between modules, such as coupling and cohesion. In the examples and assignments we've done so far, it's been pretty easy to figure out what should go in what module. We're re-implementing strings for some reason, so that should go in a module. We're making a stack, that should go in its own module. We're making a zone, that should go too. It won't always be that simple in larger projects, so we're going to talk about how to separate them and how to evaluate whether a certain separation is very good. And then this will come into play later. We'll talk about optimization a little bit, because sometimes your programs are just slow. We're going to look at some low-level optimization techniques, doing more evil hacks with bit fiddling that you probably shouldn't do in the real world. And then we'll talk about more realistic techniques that have more general utility. It basically comes down to applying what you know from Comp 2140 and similar courses and making more sweeping changes like that, which tend to have more impact than low-level solutions because the compiler is way smarter than you and is already optimizing the heck out of what you're writing. But I'm getting ahead of myself. This second learning outcome, I think, isn't even in this set of lecture slides, but we'll get to it in a later class. So as a little review, our goal with modular design is to separate our code into reusable code objects. If you're copy pasting, that's a red flag. Kinda sorta on your assignments, but definitely in the real world. If you have code that's repeated a bunch of times, that's going to become incredibly difficult to maintain. So the way of separating our code into reusable bits is, or the one that we've seen the most so far is the second one on this slide, abstract data types and data structures. String, stack, and zones all fit this description. You have a thing, an object, a noun, that should probably have its implementation details separated from the rest of the code so it's easy to change things without affecting other parts of the code. Another reason to separate parts of your code is also a reason why a subset of really good programmers will tell you that object-oriented programming is horrible and a bad idea and turns your brain to mush. And it's because you'll commonly find subsystems of functionality that don't necessarily correspond to nouns. They're more like verbs. I think malloc is a good example of it. The family of malloc functions like malloc, realloc, free, and I'm sure there are a few more. There is no memory allocator object. You might be forced to write one if you're writing an object-oriented language, but conceptually, memory allocation functionality doesn't really correspond to a noun, an object. So object-oriented programming sort of forces you to turn everything into a noun, but not everything is a noun. And the main point that I'm making is that sometimes you'll just have a group of related functionality, related verbs that you'll want to put into a module. So how do you do that? Not by lines of code in a function, lines of code in a file. You want to use a thing called the single responsibility principle. More pre-software engineering. You're going to learn a whole bunch more of these catchy names of techniques. The single responsibility principle essentially says that every part of your code should do one thing, and it should do it well. Your stack should not be a generalized stack queue hash table thingy. It just does last in, first out data storage. And it does it well, hopefully, if you did well on assignment too. And the malloc family of functions has a few different functions. They do different things, but they do well in a metric that we'll talk about soon called cohesion. It makes sense for all those little bits of functionality to be grouped together. And also importantly, each function only does one thing: allocate memory, reallocate memory, free, and whatever else things do. If instead they made a function that would allocate memory if you passed in a number and freed it if you pass in a pointer, that would probably be really difficult to program and also pretty difficult to work with, especially since everything is a number and pointers are numbers too. So of course, this lecture slide links to good old, Wikipedia, asking for donations again. You should donate to Wikipedia, they're cool. Anyway, you could read more about them, do some more early studying for software engineering by reading about all these words. Luckily, we're only going to cover single responsibility in this course. Again, there are two main targets: reusable abstract data types, ADTs, data structures, and then subsystems. That's what I've been describing when I talk about malloc. That's just one example of a subsystem. Try to think of another example of a subsystem, probably in C or maybe in Java. I think printing code or printing text to a standard output would be another subsystem, maybe in the same subsystem as accepting input. And yet more pre-software engineering. A design pattern is a, how do I define this without saying pattern? It's a technique, I guess, that tends to repeat itself across different code bases. Of course, you'll probably be implementing unique algorithms to solve unique problems, but there are some things that seem to pop up again and again, and those are design patterns. Can I get any examples? Woo! I think singleton is probably really easy to understand without taking software engineering. You ensure a class is only one instance and provide a global point of access to it. It's like a static class, except not quite. Don't grill me on the details. So if you have a subsystem like allocating memory or printing text, and you're forced to use object-oriented programming because your boss demands it, you'll probably use a singleton to implement those. So, as with all this software engineering stuff, don't worry about reading all those Wikipedia articles. We're only going to cover a small subset of these techniques and just focus on preparing you for taking the actual software engineering course. You know this. Comp 2140 is a co-requisite for this, I believe, so you're approaching the end of that and hopefully know all about lists, sets, and trees. In our particular implementation, remember, this course is not about C, but we use C. Each ADT gets a .c and a .h file. And let's talk about subsystems a bit more. It's a collection of related functionality. Aha! Yep, stdio.h. That's a subsystem. And just like the data structures you've been implementing, that stdio.h has a corresponding C file somewhere that contains the implementation of everything, the stuff that you don't have to worry about. The related functionality is grouped together as a module. You've definitely seen classes before, and you've maybe seen packages, collections of classes. So it's all grouped together based on related functionality. May use other ADTs. There's inevitable connections between subsystems. You want to minimize the amount that subsystems and ADTs depend on each other's implementation details, but you of course can't avoid them using each other's interfaces. And yeah, I'm staying one step ahead of the slides. This is silly. Each subsystem will get its own .c and .h file when we work on these things in C. Of course, it's different for every language. The technique of giving each subsystem its own file is pretty universal, works across languages. But if your subsystem has a collection of classes, you would use packages in Java, I think modules in Python. You'd group them together. So how do we define a subsystem? What do you do? Oh, you have some functionality and you're not sure how to organize it. We have two concepts, sort of two informal metrics. These are impossible to actually physically measure and get a number to optimize, but in a qualitative way, these tell you how good a subsystem is: cohesion and coupling. Cohesion is how well pieces of code and the concepts that they implement belong together. Basically, similar things should be close together. Recall the single responsibility principle. Each thing should do one thing and do it well. All those things that do one thing and do it well should be grouped together if they do similar things. If malloc was in stdlib and then free was in some other library, I don't know, call it std free, that would be low cohesion because similar things are far apart. Similarly, if printf and malloc were in the same module, that would also be poor cohesion, low cohesion, because some unrelated things are thrown together. This actually means that stdlib.h actually has pretty low cohesion. If you have anything called library or perhaps manager, that's probably a red flag for low cohesion, but sometimes you just have miscellaneous stuff and you can't avoid that. Yep, single responsibility principle. Each of the classes and each class and module should implement one concept. I'm glad I thought of those two examples. Printing stuff and memory allocation are two examples that should be put in one module. And we say that something has high cohesion, good, or low cohesion, bad. And then the related thing is coupling. This is a measurement of how much class, module, function, concept, a thing depends on other things. High coupling makes code hard to change. You decide that your string should use a linked list instead of an array, and then suddenly all of your code breaks because it turns out you've been using direct array indexing, maybe, all throughout your code. So it's bad if changes in one location affect other locations. This is like all what we're trying to avoid with separating interface and implementation. But it's impossible to completely avoid coupling. Objects, what class, modules, functions, concepts, they have to use other things, other classes, modules, functions, or concepts. So it's impossible to make something that's completely self-contained. I suppose you could achieve that complete self-containment by making your program one giant class or whatever, but you can probably see the issues with that. But we use modular design to help control or reduce coupling. We could call coupling high or low, similar to cohesion, or we could say that it's tight or loose. You could imagine just something, maybe a piece of fabric that's woven together really tightly, and then you make a cut on one little bit of it, and it affects the rest. And if you keep cutting things, it falls apart. Bad metaphor. Don't listen to that. It's kind of useless. Things that depend on each other too much are tight. Things that are mostly self-contained are loose. So these slides have a kind of silly metaphor. No, this is the most serious thing ever. Metaphor for coupling. So you know phones and headphones? And the headphone jack, my beloved, that system had pretty low coupling. You just grab some headphones off the shelf, and you know that they'll work on your phone. You don't have to know too much about the details of your phone or your headphones. It just works. Till Apple messed everything up. I like my AirPods, but I'm still salty about this. Yeah, if you want the headphone jack back, you have to drill a hole. So headphones and smartphones have high coupling now. You want some headphones, wired ones especially, you need to know, until late last year, you would need to know the operating system of your phone, if it's iOS or Android, in order to get compatible headphones. But now it's even slightly more complicated because iPhone 15s have USB-C. Good for them, took way too long, but I'm happy about that. But now it's even more coupled. You need to know what kind of phone you have, and also if you have an iPhone, how new it is, and then make sure that your headphones correspond correctly to the phone. You can also get adapters, but that is really a Band-Aid solution. You still have to get the right adapter for your model. And wait, I don't want to move on to that other example quite yet. So this whole rant about headphones and phones serves as a nice metaphor for tight coupling. Before, you didn't need to know much about the details about the phone and headphone in order to listen to music with a wire. Now you do. And then an example of low coupling is paying for stuff. I think there are two major credit card brands, Visa and MasterCard. I don't know the details, and I don't have to. 99% of the time, you go to a merchant and they accept both. There are almost certainly some really complicated financial things going on behind the scenes that differ for Visa and MasterCard, but as a customer, you don't need to worry about it. It's loose coupling. So now we're going to do a quiz. I have some more examples of real-world things that are tightly and loosely coupled, and you're going to try to identify it. There are some regular questions first, though. This will probably take up the last 15 minutes of class, so it's all good. Please don't show the answers. Okay, phew. I'll just wait a few minutes for people to join and we'll get going. I was just about to say, okay, 9 players, that looks good. But every time I say that it's slowing down, a few people join, and then you guys preempted me. So I'll just keep this screen open until no one joins for 30 seconds or so. Are there even 13 people in this room? Oh yeah, that's plenty. Oh. Now I think one person joined and two left. I'm just gonna stay here a while longer. Okay, looks like it's been on 12 for the last little while. This is your last call. Let's get started. Oh no, hold on. There we go. Good luck. This is a goal, not the goal. There are multiple good answers. Nice. I think the one that got the most answers, or the most votes, is the closest thing to the goal of modular design. You want stuff to be easier to reuse. The other correct answers are sort of how we do it. And yeah, hiding implementation details is important. You should remember that. Oh, now we're back to 14th place. 15. Crazy. We're doing numbers. Awesome. Aw. Those two people about saying that clients should know what's inside their object. No, those are implementation details. If it's important for a client to get specific variables, use getters and setters. Those make it so, I don't know, you change how something is stored, maybe the type. You could keep your interface the exact same still. Nice. Not much to say about this. They should know the interface and not the implementation. Good job. Beyonce? Congratulations. I think this is the end of the objective questions. Now we're going to get a bit more creative. I think. Oh no, question 404. Still doing this. Cool. You should definitely care about how you're implementing your interface. You're the one writing the code. And your mom and dad probably shouldn't care about how you're implementing your interface. That's maybe correct depending on how tech savvy your parents are, but it's not the best answer. And then the last two, the wording probably tripped a few people up. The majority of you have the right idea. You can change the implementation without affecting the rest of your code. And then the two that got it wrong probably also had the right idea, but got the word wrong. Interface is the thing that everyone else knows about. Implementation is a secret. Ooh, Snuggles must have answered fast. But Beyonce's still winning. Congrats. Okay, now we're on to the more abstract stuff. Is Lego coupled? Is it cohesive? Relative to what? Take your best guess. There's no right or wrong answer for this. It's all up to interpretation. So someone says it's loosely coupled and highly cohesive. I won't comment until we've gotten a few more votes. Why does it just say 1 despite having a whole bunch of these points? Yeah, Menti. Oh, because it's the first option. Okay, so I would definitely agree that Lego has high cohesion, especially the bricks that are specifically in this image, so no Technic or CCBS or anything. Everything fits together nicely. Coupling, that's a little weirder. I choose to interpret this as coupling between Lego pieces. And in that case, and this specific example, there's actually more Lego later in this quiz. I would guess that it's pretty loose. They're just bricks and studs. You don't really need to know anything about, I don't know, the plastic molding process in order to put Lego bricks together. But it's all very subjective, as always. So we're going to talk about more Lego, but notice that there's different Lego. The bricks have weird shapes. There's even a Bionicle foot in there. Oh, and a Bionicle 2 legs and an arm. Sweet. Some plants, some Knight's Kingdom armor, some minifigure armor. This is different. How do you interpret that? Pretty good answers again. I would definitely agree that this example is a lot less cohesive than the bricks. Like if you compare Lego bricks and the CCBS system used in the older Lego action figures, it's like they're completely different systems. They don't really fit together very nicely. The old Lego action figure stuff, like 2006-ish Bionicle, that was like very difficult to work with both that and bricks at the same time. Low cohesion. Tight coupling, I agree with as well. You're no longer just connecting bricks to other bricks. There are now those axle and pin connectors from Technic, ball joints, probably a whole bunch of other things. You now have to know more about how the pieces fit together in order to make anything useful. Now what about this webcam? we have about 30 seconds left, so I'm going to start explaining before waiting for more stuff to come in. Loose coupling, probably agree with. As long as your computer has a USB port, you're probably good to go. But there may be complication in operating system drivers and USB-A versus USB-C. Cohesion is just weird. It's only one object. You could say that maybe it fits together well with the rest of a computer because that's related functionality, but this is sort of intentionally obtuse and hard to answer. So I think we have a couple more cases. I'm not sure if we'll continue this next class, but this is definitely it for this class. Have fun on the assignment, and have a good day.